Hey, what's up you lot, Path here, and today I'm making a video that I've been wanting to make for a really long time. Now, like many of you watching this video, I have grown up with the internet. I've grown up with websites like YouTube and Wikipedia in particular that have really shaped my learning, not just in terms of academic learning, but in terms of, skills that I've acquired. For example, I learned how to play guitar and drums straight off YouTube. My passion for physics was even furthered by reading lots of Wikipedia pages about certain topics in physics. And so I'm really grateful that I could have the internet whilst I was growing up, but particularly YouTube and Wikipedia. Oh, and by the way, just as a side note, when your teachers tell you Wikipedia is not really useful, yeah, it's not useful for high school level and for college level, but as soon as you get to university, it becomes a lot more useful than you'd ever realize. Now, if you don't want to just watch me ramble for the first couple of minutes, then skip to this timestamp here. But otherwise, I just quickly want to chat about the reason that I wanted to make this video. But anyway, so like I said, I grew up with the internet. I grew up with YouTube, I grew up with Wikipedia, and I was learning a lot from both of these websites. And around the time that I started getting interested in physics, as you'd expect, Wikipedia was a really valuable resource when it came to understanding complicated physics concepts, stuff that I'd never heard of before, stuff that seemed very esoteric. And in quite a few of the cases, I would go onto the Wikipedia page, read a few paragraphs, and have learned something by the end of it. However, in quite a few instances, that was not the case. Because if you go onto certain Wikipedia pages, especially physics-related ones, at least those are the ones that I know about, you'll see something like this. The Schrödinger equation is a linear partial differential equation that describes the wave function or state function of a quantum mechanical system. Yeah, how is a 15-year-old meant to understand any of that? Now granted, if you're somebody that's approaching the end of high school or the end of college in the UK, about to go into university basically, then you will understand some of that. You'll know some of the words and you'll know what they mean. However, quite a few times these Wikipedia pages were aimed at people who were studying the subject, which is fair enough, right? But today I want to change that a little bit. So I'm going to take this page, the one that I've just read out to you, the one on the Schrödinger equation, and break down the first couple of paragraphs so that hopefully anyone will be able to understand it. Now it's worth noting that I'm not actually going to explain the intricacies of Schrödinger's equation here. I've already done that in a previous video, and if you haven't seen it, check it out up here. In that video, I tried to break down Schrödinger's equation for lay people, for somebody who hadn't studied it before, without going into the full details of the math, but still understanding some of the intricacies. But anyway, so let's go back to this Wikipedia page and let's look at the very first sentence on this page. The Schrödinger equation is a linear partial differential equation that describes a wave function or state function of a quantum mechanical system. Oh boy. The first few words. The Schrödinger equation is a. Perfectly fine. We already know that we're on a Wikipedia page about the Schrödinger equation. Linear partial differential equation. Now, after those 4 words, I guess that most of you will have heard of the word equation, so I'm not going to discuss that one here, but I am going to talk about linear partial differential. Now, these words aren't actually that difficult to understand, at least on the surface level, so let's go into it. First of all, what is a differential equation? Well, we can think of a differential equation basically as one which contains a derivative in it. And a derivative is actually something that I've discussed in previous videos, but very quickly as a recap, I'm going to give you an example. Let's say that we want to calculate the velocity of this object moving towards the left. Well, in that case, we can recall that the velocity of this object is equal to the distance it moves divided by the time taken for it to move that distance. In other words, the change in distance from start to finish divided by the time interval or the change in time from start to finish. Delta x divided by delta t. Now this equation is all well and good if the object is moving in a straight line at a constant speed, then we can calculate its speed. However, what if this object was to start slowly at first, then speed up, then slow down, and so on and so forth? What if its distance by time graph looks something like this? Well, in that case, we can work out its average velocity using the original equation I gave you. We can say that the average velocity is equal to the total distance covered divided by the total time taken for that distance to be covered. But finding the velocity of the object at every individual point along its journey is a little bit more difficult. And this is where the derivative comes in. If we take this function, this curve that we've drawn to represent the distance traveled by the object over time, and we take its derivative, in other words, if we find the gradient of this curve at every single point along the curve, then we will have a curve representing the velocity of the object. And this velocity is the derivative, dx by dt, of the distance traveled by the object. And so a differential equation is simply one that contains a derivative of a dependent variable. We're finding the rate of change of that dependent variable with respect to the independent variable. So in the case of velocity, we're finding the rate of change of distance with respect to time, or in other words, how quickly the distance changes over time. So that's what a differential equation is. Now, what's a partial differential equation? Well, when we take a certain function, let's now go back to our velocity description, we know that that function depends in this case on time, because the distance moved by the object is dependent on what time it is. So right at the beginning, the distance moved by the object is 0, 5 seconds later it's moved maybe 5 meters, who knows, but it's dependent on the point in time that we're considering the object's distance. In some cases though, certain dependent variables don't just depend on one variable. So coming back to the Schrödinger equation, this equation is actually dealing with the wave function of a quantum system. We'll come back to what that means in a second, but basically our quantum system could even be something like an electron. Now the wave function is directly related to the probability of us finding that electron in a certain place at a certain point in time. In other words, this wave function is dependent on the position that we look at and the time at which we look at that position, and tells us the probability of us finding that electron at that position at that point in time. And so our wave function is a variable that depends on position and on time as well. Well, in that case, we could take its derivative with respect to position or with respect to time. But a partial derivative only takes the derivative with respect to one of those variables and completely ignores the dependence on the other variable. So in this case, we're taking the derivative of the wave function, psi, with respect to time, and we're ignoring the dependence on the position. That's just on the left-hand side of the equation though. So a partial differential equation, relatively simple. When we take a derivative, we just take it with respect to one variable and ignore the others. What is a linear partial differential equation? Oh, I've just remembered, by the way, you know when you go on Wikipedia to try and learn something and then you see a sentence like this right at the beginning, and then you don't know what's going on, so you try and understand some of the words in this sentence. So let's say you click on the word linear, for example, and then you can't understand it at all either because it's exactly the same. Complicated words tailored for people who are actually studying the subject. In mathematics, a linear differential equation is a differential equation that is defined by a linear polynomial.
Oh, wow, score! Look at this. This is an aspen. You can tell that it's an aspen tree because of the way it is. Wow.
Ah, man, I should not have done that. Anyway, that's so sick. All right. Anyway, yeah, cool. But yeah, common frustration of Wikipedia sometimes when you're trying to understand a certain topic and you click on the words to try and understand what those words mean, and then you get into this rabbit hole of just clicking on more and more and more Wikipedia pages until you eventually can't remember where you started. Anyway, linear partial differential equation. Now, the word linear is actually relatively simple in this instance as well. A linear partial differential equation basically only deals with a function and its derivatives to the first power. In other words, we're never going to see psi squared in this equation, or d psi by dt squared, or d psi by dt cubed, or cosine of psi, or sine of psi, or anything like that. Every time we see psi or d psi by dt, we're never going to see it squared or cubed or to any other power than 1, and we're not going to see sine of psi, cosine of psi, that's really hard to say, or anything like that. It's just going to be a polynomial of order 1. So that is a linear partial differential equation. Now, this linear partial differential equation deals with the wave function, and as we've already said, the wave function of a quantum system basically deals with, or is directly related to, the probability distribution of that quantum system. It is basically just a mathematical description of our quantum system, whatever we're dealing with in that case. It's meant to be the complete set of information that we have about that quantum system. In other words, if we know a quantum system's wave function, then we know everything that we possibly can know about that quantum system. This is discussed in a little bit more detail in my Schrödinger equation video, so go check it out once again if you haven't seen it already. Now, a quantum mechanical system is just a system that deals with very, very small particles. It could be anything like a single electron, or maybe an electron orbiting a proton, which is a hydrogen atom, or for that matter, slightly more complicated things, but generally small-scale stuff, because quantum mechanics at the moment is best at dealing with small-scale stuff. Okay, so we've explained the first sentence. The second sentence, then. It is a key result in quantum mechanics, okay, fairly self-explanatory, and its discovery was a significant landmark in the development of the subject. So yeah, the Schrödinger equation is basically a very, very important part of quantum mechanics. The equation is named after Erwin Schrödinger. Hopefully I'm pronouncing his name at least slightly correctly. who postulated this equation in 1925 and published it in 1926, forming the basis for the work that resulted in his Nobel Prize in Physics in 1933. Now, interestingly, Schrödinger actually postulated this equation. In other words, he actually came up with it and then took it as an assumption for the rest of his calculations. Now, the reason that we can do this in science is because, we could come up with any theory that potentially explains the universe that we want, and then we test that theory with experimental evidence. Now, with quantum mechanics, is actually based on a huge number of postulates, like more than you'd expect. Something like 7 or 8. I can't remember exactly how many. I'm probably going to get crucified in the comments for not remembering. But the idea is that quantum mechanics is almost entirely based on these assumptions about certain ideas. So, for example, the idea that the wave function is directly related to the probability distribution of a quantum system is a postulate of quantum mechanics. It's an assumption. And once again, the reason we can do this is because we can make whatever assumptions we want, do the maths, see where the theory takes us, and then we test that theory. Now, a reason that a lot of people rejected quantum mechanics at first is because, firstly, it doesn't align with our idea of common sense. It doesn't really make logical sense to us. And secondly, these postulates seemed really wild. They just seemed crazy, unusual. So a lot of people just thought, okay, well, this makes no sense. We're just going to ignore it completely. The problem is that quantum mechanics basically aligns perfectly with every single experiment that we've done so far. When you take these assumptions and you do the maths and you follow the hypothesis through, then you have something that is testable, because that maths that you've done will produce something that you could test in real life. And every single test that's been done so far aligns perfectly with the predictions of quantum mechanics, annoyingly. So even though it doesn't make any logical sense to us, it's the best thing we have in terms of predicting what will happen on a small scale. Quantum mechanics has not been wrong so far on the small scale. Every experiment we've done has aligned with the predictions perfectly. Anyway, so the second paragraph of this Wikipedia article, coming back to this, likens Schrödinger's equation to Newton's second law of motion, which is what we had when classical physics was still a thing. I mean, it still is a thing, but, when it was the dominant thing in physics, when people thought that that was the correct way to go before quantum mechanics came along. In classical mechanics, Newton's second law, F is equal to ma, is used to make a mathematical prediction as to what path a given physical system will take over time following a set of known initial conditions. In other words, if we're following a particle and we know what state it was in initially, whether it was sitting here or it was moving around at this velocity at the beginning in this direction, then we can use Newton's second law of motion to predict what will happen later. Solving this equation gives the position and the momentum of the physical system as a function of the external force F on the system. So once again, if our system is the particle, then we could solve this equation, and that would give us the position of this particle at a certain point in time, as well as the momentum as a function of the external force, of the force that we apply to this particle. Those two parameters, the position and the momentum, are sufficient to describe its state at each time instant. In other words, if we know its position and momentum at every point in time, then we know everything that we can know about that particle and its motion. In quantum mechanics, the analog of Newton's second law is Schrödinger's equation. In other words, Schrödinger's equation does to quantum mechanics what Newton's second law did to classical physics. The concept of a wave function is a fundamental postulate of quantum mechanics. There we go, that's what I said earlier. It's an assumption that we've made when building the theory of quantum mechanics. The wave function defines the state of the system at each spatial point and time. So it tells us some information about the system at every single point in space and every single point in time, specifically directly related to the probability of us finding certain particles in the system, for example, at those positions and at that point in time. But it gets a lot more complicated than that. I'm just not going into too much detail about this. Using these postulates, Schrödinger's equation can be derived from the fact that the time evolution operator must be unitary and must therefore be generated by the exponential of a self-adjoint operator, which is the quantum Hamiltonian. The derivation is explained below. Yeah, not today. But do you see what I mean? Like, this is not something that anybody could just walk into this page and understand what it means. Now, I don't know if I've mentioned this already, but I do know that simple Wikipedia exists, like Wikipedia in simple English, and the Schrödinger equation page on simple.wikipedia.org is actually quite interesting to read. I know that this exists, but I wanted to make this video anyway to try and explain it from a physicist's perspective, or at least from the perspective of someone who's done a physics degree and still calls themselves a physicist, even though I'm not a researcher in any way. But yeah, so if you want to read more about the Schrödinger equation and you're not a physicist, check out the simple Wikipedia page. But anyway, so I'm going to end this video here. Thank you so much for watching, and if you want me to do this with more Wikipedia pages about physics, then please send me a link down below. I know that this has happened to me quite a few times and I only went through one example here, but it'd be interesting to see the Wikipedia pages that you're struggling with. So yeah, link me down below as well. And since this is a shorter video than the previous one I made, which was a 20-minute video on one of the Maxwell equations, watch it if you haven't already, I'm quite proud of that one. But since this is a short video, I am going to do my weekly question of the week. I haven't done this in ages, so I might be a bit rusty on this question, but I want you to tell me, what's the one thing that you've done over the past few months, let's say past 3 months, that you're really proud of? For me, it's got to be finally getting the motivation back to get on the grind in terms of YouTube, in terms of music. I finally started recording some music again, which I'm really happy about. I've been wanting to do it for such a long time, but like I say, I've been working hard, at work, and I haven't had as much time for YouTube, for music, for badminton as I'd like to have. But I feel that motivation coming back slowly and I'm putting more time into that, devoting more time into my passions, my hobbies. So I'm quite proud that I'm getting back onto it again. Tell me what it is for you. What have you done that you're the most proud of over the past 3 months or so? Let me know in the comments down below. Thank you so much for watching and I will see you really soon. Bye 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 bye.